Hello, my name is Sasha, and my team partner Justine, Steven, and I looked at using probes on a small language model to detect distracting information in math problems. And this is an interesting problem because, as I'm sure many of us have experienced, uh, large language models often fail at mathematical reasoning, and at least one source of these errors is irrelevant and distracting information. So concretely, we took in word problems which contained and didn't contain irrelevant information, and we used probes on the layers of a small language model to train classifiers. And we used synthetic data for training because existing data sets just weren't large enough for training and validation and testing. And the feature that we used were the layers, the activations from the layers of Llama 8 billion parameters specifically. So we're able to train 31 probes, one for each layer. And each of these layers produces a vector of 4096 dimensions per token. And we limited ourselves to a maximum sequence length of 512 tokens. So you end up with this massive tensor. And to make this problem tractable, we experimented with different pooling techniques over the sequence length, specifically just by taking the last token representation, also taking the mean and the variance over the sequence. We also experimented with different base language models, so the vanilla Llama versus an open math fine-tuned variance. We experimented with more complex probes, so small neural networks. We also had the insight that we could save the activations from Llama when we pass examples in, because those activations won't change because we're not fine-tuning Llama itself. And this sped up our iteration and training speed dramatically and actually made this problem a lot more tractable. In our experiments, we found that variance pooling worked the best, although all the pooling methods that we tried worked pretty well. And we experimented with different classification thresholds to see which ones maximize the F1 score. And interestingly, because we tested on a different data set than we validated on, the classification thresholds that were optimal were different. And so just assuming a 0.5 threshold, instead of trying to tune this on the validation set as a hyperparameter, worked the best. Most interestingly, we found a direct correlation between the probe layer depth and the AOC, so the area under this curve, which is a very good metric of how well the model is performing while taking into account different possible classification thresholds. And this makes sense because, as we know, later layers are able to learn higher level, more abstract semantic information, like does this problem contain something distracting or something irrelevant. So in conclusion, we found that linear probes were sufficient to detect relevant information, with deeper layers being more showing better performance and maybe learning faster. And we did some experiments and we found that you could use a result like this to modify prompts and recover some of the performance that you lose by having irrelevant information. And in the future, it would be interesting to try to apply probing approaches to other sorts of reasoning challenges. We could try to improve our synthetic data set to have more variety in the type of distractions that it's being shown. We could try different pooling methods and see how they perform on different types of challenging problems. It would also be very interesting to see what kind of gain we get from using even larger language models, and if the computation is worth it, and also trying to integrate these small gating classifiers into more complex systems or agentic systems.